We will start our problem with a triangle. Then we will divide this triangle using two lines pulled from two vertices of this triangle up until the opposite sides, and therefore we will split this triangle into four separate areas. Three of those areas will also be triangles with the areas of 10, 20, and 15 squared units. The question is, can we somehow calculate the remaining red area of this triangle? If you want to answer this interesting question for yourself, you can pause the video right now and then come back and check the solution. Alright, so let's solve this one. In this video, I will offer you three different methods to solve this problem. The first method will be the triangle relations. We're going to start this method by first pulling a line from the intersection point of our two lines up until the remaining vertex of our triangle. In this way, we have divided the remaining area into two triangles whose areas we're going to label as A1 and A2. Now, let's use one really interesting triangle theorem that states that if two triangles share the same height, then the ratio of their areas is equal to the ratio of their bases. So let's use this in our case. First, let's take a look at this red triangle, and let's label its base as A. And let's also have a look at this blue triangle right beside him, and let's label its base as B. You can see that both of those triangles share the same height, so we can use our theorem. We can say that the relation between their areas is equal to the relation between their bases. Now we can simplify the numerator and get the following. Now let's find two more triangles. Let's have a look at the bottom red triangle with the area of 10. It also has the same base of A, and if you take a look at the triangle right next to him, you can see that it has the same height and it has the base of B. So we can use the same theorem again and say that the relation between their areas is equal to the relation between their bases. Now, if you take a look at our equations, you can see that both of those equations have the same value. So this means that those two equations are equal. Now we can just work through this. We can first cross-multiply this to get the following. Now we can expand the right side and then rearrange the terms to get the following. Now we can simplify our equation by dividing everything with 10, and we will get that 2a1 minus a2 is equal to 15, and this is our first equation. Now let's find another one by using the same theorem again. This time let's have a look at our new red triangle, and let's label its upper base as A. Then let's have a look at the bottom blue triangle and let's label its base as B. Looking from the bases A and B, you can see that both of those triangles share the same height again, so we can use our theorem. We can say that the relation between their areas is equal to the relation between their bases, and again we will simplify the numerator and get the following. Now let's find another equation. Let's use the upper triangle with the area of 15, which has the same base of A, and the triangle below him with area A2, which has the base of B. Those two triangles share the same height, so we can use the same rule that the relation between their areas is equal to A over B. Since both of our equations are equal to A over B, we can conclude that those two equations are also equal to each other. Now we can again cross-multiply this and get the following. From here we will expand the right side of the equation, then rearrange the terms and simplify everything with 5 to get that minus 3a1 plus 4a2 is equal to 30. Now we have a system of two equations with two unknowns, and you can use multiple methods to solve this system. I will just expand the top one with 4 and get the following. Now we can just add those two equations together, and you can see that both second terms on the right will cancel each other out, and we will get that 5a1 is equal to 90, which means that the area A1 is equal to 18 squared units. Now we can just put this value back in any of our equations to find A2, and in this video I will choose the first one. So 2 times 18 minus A2 is equal to 15, and we can work through this and finally get that the area A2 is equal to 21 squared units. Now it's pretty easy to find the red area, as it is equal to the sum of both areas A1 and A2. So in our case this is 18 plus 21, which means that the wanted red area must be equal to 39 squared units, and this is our solution. Alright, so now let me show you the second method, which is quite interesting, and it will use the Menelaus Theorem. The Menelaus of Alexandria was actually a great Greek mathematician and astronomer, and in some way we will pay the homage for this great man by using his theorem to solve our problem. We will start by labeling all the vertices of our triangle as A, B, and C. Then we will label the bottom intersection point with the line AB as D, and we will label the right intersection point with the line CB as E. Finally, we will label the intersection point between our two lines as O. Now let's use the Menelaus theorem, which actually relates ratios obtained by a line cutting the sides of a triangle. So we will start this theorem with a triangle from which we will pull 3 extensions of its lines, just as you can see on the sketch. Then we will pull another red line which cuts through those 3 extensions outside of the triangle, as you can see on the sketch on the right. Now let's label all the vertices of the triangle and all intersection points. From here, Menelaus' theorem states that the product of the relations between the segments OA, AE, BE, BC, and CD and OD must be equal to 1. Now, if you notice, I have labeled the sketch on the right the same way as the sketch on the left, so that we can avoid any sort of confusion. In this way, we can notice that the triangle OAC on the right is actually this green triangle, and the line AB, which is the base of our triangle, is our red cutting line. So we can use the Menelaus theorem. But if you notice, we do not have the values of those segments. But we can find those values by again using the same theorem of a triangle which we used in our first method, that the relation between the areas of the triangles with the same height is equal to the relation between their bases. So, with this in mind, let's first label the remaining area of the quadrilateral ODBE as A. Then, let's have a look at our relations. First, let's have a look at the line AO. You can see that this line is actually the base of the triangle AOC. So, instead of the line AO on the right, we will write down the value of this area, which is 20. Now, if you have a look at the line AE, it will be the base of the triangle AEC. But this triangle AEC will actually have the same height as our previous triangle AOC. So this means that we can use our triangle theorem to replace the value of AE for this overall blue area of 35. Now let's just do the same thing for the remaining lines. If you have a look at the line BE next, you can see that it is the base of the triangle AEB. So we can write this area as A plus 10. Next, we will take a look at the line BC, which is actually the base of the whole triangle ABC, which has the overall area of A plus 45. Those two triangles again share the same height, so we can use those areas. Now finally, let's take a look at the line CD. You can see that this line is the base of this blue triangle ADC with the overall area of 30, so we're going to substitute this value. And finally, the line OD will be the base of the triangle ADO with the area of 10, which has the same height as the previous triangle, so we can replace the value of OD with the area of 10. Alright, so now let's work through this equation by first simplifying everything, and then we will get to the following. Since the relation between the numerator and denominator is equal to 1, this means that those two values must be equal to each other. Now, we will just expand this equation and get to the following, then we will rearrange the terms, and finally get that our red area must be equal to 39 squared units again, and we have our solution. Alright, so let me show you the method number 3, which is actually a great one, and it will use the ladder theorem. This theorem is actually excellent for this kind of a problem because it is quite specific and it is almost perfectly made for this problem. This theorem states that if you have any triangle and you divide it with two lines pulled from the two vertices of a triangle, and you divide this triangle in 4 separate areas, from which 3 areas will be triangles with the areas A, B, and C, you can say that the sum of the reciprocal value of the area of whole triangle and the reciprocal value of the area of the middle triangle is equal to the sum of the reciprocal value of the overall area of the left and the middle triangle and the reciprocal value of the overall area of the middle and the right triangle. So we can use this in our case. You can see that the middle triangle in our case has the area of 20. This corresponds to a triangle B on the right, and in this case A will be equal to 15 and C will be equal to 10. So we can just substitute those values from our sketch. Now all that we need to do is to work through this equation to find the overall area of the whole triangle. So we will simplify this a little bit, then we will find the common denominator and simplify once more. Now we will just cross-multiply this and get our new equation. We can simplify both sides with 10 and expand to get to the following. From here, we will get that 5 times the area of overall triangle is equal to 420, which means that the area of the overall triangle is equal to 84. Now it's pretty easy for us to find the remaining red area, since it is equal to the difference between the overall area of the triangle and the sum of those 3 triangles inside of it. So if we substitute the values and calculate, we will get that this red area is equal to 39 squared units, and again we have our solution. Alright, so I really hope you guys enjoyed this problem. If you did, do not hesitate to leave a like or subscribe to the channel. Those stuff really means a lot. Of course, if you found another way to solve this particular problem, please write me down in the comment section below. I always love to see when community finds another interesting way to solve the problem. And of course, until next time, see you all and take care.